The broadcast is now starting. All attendees are in listen-only mode.
Well, let's see what's wrong here. People can see you, and now they can hear me. How do you like that? So, let's see if we could start the music. Well, that was John Denver. And I'm really not a pirate. I'm Dr. John Minarsik. But I thought I would put this on today because, this will be our very last session before Halloween, that pagan holiday where everybody worships the devil. And I thought it might be a fun way to start the webinar off today. Today's webinar, I don't know how to start it. I don't know what to say by way of introduction, but I always go crazy when I start to talk about genetic diseases or genetic disorders. And I guess I could tell you why. Well, I'll tell you why by showing you our first PowerPoint, okay? Let's go to it. Let's see if we still have it here somewhere. Here it is. Genetics and genetic diseases in general is a topic that evokes horror like Halloween in just about everybody, and anxiety and dread. Because genetics are a topic that everybody feels inadequate in. even if you just graduated from medical school or residency or a molecular fellowship, you're going to feel totally insecure and inadequate because things change so fast. That was horror number one. Horror number two is I know a handful of guys that really, really keep up to date with this stuff and they know about it. And I probably could have had them here talking about it. But the problem is, most people that are really, really up to date on genetics don't really know how to explain it. So that's what I have been saying by way of introduction for the last several years. And I'm going to try to do a decent job again to go down to a actual human being level, not alien level like most of the genetics pros are, and talk about genetic disorders or genetic diseases. And I know what you're thinking already. We are thinking, aren't all diseases genetic? Well, in a way they are, aren't they? Because our genome determines our susceptibility to diseases depending on the environment. So for many, many years, there was always a big discussion about are diseases genetic or environmental. Actually, the answer is pretty obvious. It's both. We have a genome, 3 billion base pairs or something like that. And depending on our exposure to the environment, we are subject to just about every disease, we could think of. So let's talk about our mutations. Let's talk about our genes. We have thousands and thousands of them. And I said something like the average gene could be like 20 to 30 to even up to 1 million base pairs. We got about 3.2 billion base pairs altogether. That's our genome, and changes in it, whether they are acquired or inherited, are called mutations. So mutations determine our susceptibility to disease. A mutation is a permanent change in DNA. It could involve a very large portion of our genome, like an entire chromosome, for example, if we have an extra one or if we have a missing one. Or in many cases, it could involve part of a chromosome. This may be visible sometimes on even some of the simple stains, or it may require some molecular probes or a method here I'll be talking about later called FISH. Or it may, and very often, just involves a single base pair. It could be a deletion of a single base or a substitution of a single base. Well, you know what the bases are. I don't have to go over that. Adenine, thymine, blah, 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 blah. One of those missing could cause a major disease. And always, probably the best example of that, and the one I've always used, and many, many are like this, is an example of GAG. That's guanine, adenine, guanine. It's part of your DNA chain, which codes for the beta chain of hemoglobin. Hemoglobin has both heme and globin globin has the beta and alpha chains. And here's a beta chain. Now, in this case, if there is a single point mutation or a single substitution, let's say, of a uracil for adenine in the DNA, which carries over into the messenger RNA, you then have a GAG, which normally should be present, but now in a point mutation, you have a GUG. Remember, 3 base pairs, trinucleotides code for an amino acid. So rather than having a glutamic acid in your beta chain, you now have a valine. And on the basis of that, you have a different amino acid, a different protein, and a different type of hemoglobin called hemoglobin S. This is exactly the genetic nature of the cause of sickle cell disease. So, how are all the ways that a gene mutation may cause problems. Well, we saw one. The first one is the substitution of a single amino acid causing a major disease. But remember, a very large portion of our DNA does not code for proteins or polypeptides. What it does is it regulates, or it has processes like transcription. And remember, there's a whole bunch of DNA. We just don't know what it does. Some people refer to it as junk DNA, but I'm sure it's important. So besides coding or making abnormal proteins or polypeptides, okay, it could cause a problem with regulation, like transcription, for example. Now, if the mutation is not an exact multiple of 3, obviously, because it takes 3 nucleotides to code for 1 amino acid, then the whole lattice changes, okay, moves down or moves up, called a frame shift mutation, in which there are deletions or insertions which are not multiple of 3. And also another thing that happens, and we're discovering more and more diseases that happens, is that you can have a mutation in which there is a repeat of a certain code. Like, for example, cytosine, guanine. That could be repeat itself over and over and over and over again, thousands of times, okay? So that's another way a gene mutation can occur, as a trinucleotide repeat, okay? Not just a deletion or insertion which changes the whole lattice or the frame of the DNA molecule, not just in regulatory processes like transcription, and certainly not just a substitution of one amino acid for another in a polypeptide or protein, let's say. So, gene mutations, they could interfere with protein synthesis. They could cause an excess of it. They could cause a lack of it. They could cause a defective type of protein, which doesn't function the way it should, producing a wide variety of diseases. If it's a regulatory mutation, it could suppress the transcription of DNA to messenger RNA, or produce an abnormal type of mRNA. Well, isn't that obvious or logical that if you have abnormal DNA because of mutation, it's going to be an abnormal messenger RNA too? And that, of course, will then carry over into translation, where we're actually, making these substances or proteins at the ribosome sites. Or it could cause abnormal proteins without necessarily impairing the synthesis. You could have just as much of a protein being made, but it's chemically abnormal. It doesn't have the right structure. Okay. So, when we talk about gene mutations, and this is the way our discussion is going to go today, we could talk about them as a single gene mutation, following the classical, Mendelian inheritance, where, one gene has an allele, okay, according to Mendel, and if you have 2 abnormal ones, that's called homozygous. If the only one is abnormal, it's called heterozygous. And there are dominant and recessive diseases based on whether the abnormality is homozygous or heterozygous, based on the matching chromosome complement. And then we'll talk about a lesser well-known, but probably much, much wider topic called multifactorial inheritance. We're going to show you a lot of diseases that are caused by a single gene. We'll give you the name of the gene, okay? But what if we know that there are probably many, many, many more diseases, almost to the point of perhaps almost every disease, which are multigenic or multifactorial? Well, the situation is, we're not going to say that a certain disease is due to this gene, and this gene, and name them out and localize them. We're just going to say that it runs in the family, and we know it's not exactly one gene, but we're not going to go beyond that. Of course, genetic disorders can also include the chromosomal disorders. And when we talk about the chromosomal disorders, later on today, you always have to think of a chromosome as a string, because that's what it is. And it's a string of millions of nucleotides, okay? And it has one end, and it has another end, and it has an area in the center called the centromere, okay? And that string can have a missing portion. It could have an inverted portion. It could have a portion that came from its complement. It could be a ring structure. So if you just think of a chromosome as a string, that would probably be the best way to understand chromosomal disorders. Remember that monk, Gregor Mendel, who figured out the entire scope of human inheritance patterns? He says that we know that chromosomes pair up. We know that a gene on one chromosome is complemented by another locus or part of a chromosome called an allele. Okay, this is something you probably learned in 3rd grade. And if only one allele is abnormal and produces a disease, it doesn't matter about the other one, that's autosomal dominant disease. If a disease is caused by 2 abnormal genetic loci, alleles, then that's autosomal recessive. And, there's a whole list of autosomal dominant, autosomal recessive diseases, and they all have certain clinical features that differentiate one from another. So I'm going to give you a list of the classical things which give you the hint that it's an autosomal dominant disease rather than an autosomal recessive. And then the third type of Mendelian inheritance disease is sex-linked, and that's strictly a mutation, an abnormality involving the X chromosome, okay? And the Y chromosome is not the complement of the X chromosome, as in the autosomes, okay? So, in autosomal dominant Mendelian disease, the disease is heterozygous. It's in heterozygotes, okay? Now, the thing is, it may be a new mutation. It doesn't necessarily have to be inherited. Whereas with the autosomal recessive, it's almost always inherited, okay? Now, these 2 other features about autosomal dominant genetic diseases is that it looks like these are pretty much related. They talk about a reduced penetrance or a reduced force of the genetic abnormality, okay? So this could be greatly modified by other genes or the environment. And of course, this is related a lot to variable expressivity as well. And I would say the reason why it might be a reduced penetrance and variable expressions is simply because it's only, one allele that technically is abnormal. Another feature of autosomal dominant diseases is that very, very often they do not occur instantly. Most of the autosomal recessive diseases occur instantly, childhood diseases, but the autosomal dominants may not be expressed for many, many years. And in an autosomal dominant disease, usually result in a reduced production or an inactive protein, if we're talking about a mutation that's in a coding sequence. Now, what do these 5 or 6 things all have in common? What they all have in common is that the defect is only on one chromosome. It's heterozygous, okay? And if you could visualize a disease being present because it's homozygous, or what we call autosomal recessive, then all of these things are practically stronger or more powerful. And we're going to see that when we look at the list of autosomal recessive diseases. This is a good laundry list, and probably during the course of this year and even the course of today, we'll be talking about some of these diseases. Some of them we've already mentioned. Like Ehlers-Danlos, we talked about collagen, or osteogenesis perfecta. Okay, we talked about von Willebrand's disease. Okay, but these are all autosomal dominant diseases. I think it would be crazy if you tried to memorize it. But what do they generally all share in common? What they all share in common is that these have these features. You know, there's a wide variation of clinical expression. They're not always instantly present at birth. In most cases, usually, there's a reduced production or an inactive protein, okay? And very, very often, the mutations that you see in these diseases are acquired. They're not always necessarily inherited. So these are the features of autosomal dominant diseases. It looks like a pretty big list, but I would like to tell you that when we get to the list of autosomal recessive diseases, it's much, 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 much bigger, okay? And if you would probably imagine, because we talked about the autosomal dominant perhaps not appearing until adulthood, for example, and the autosomal recessive, because now you have two abnormal guys facing each other, it very often it's pretty close to the list of childhood genetic diseases because you see them early in life. Okay, here's an autosomal dominant pedigree, and it should make sense because remember, all it takes is one abnormal allele to produce the disease. So it's not going to skip generations, is it? Because if you have some people, chances are 50-50, you know, that they're going to be passing it on, and it's not likely that it's going to skip generations. So a genetic disease in which was present in generations after generations is probably autosomal dominant and probably has all these other features as well. Okay, so let's go theoretically now to a situation, a Mendelian situation, in which we have a homozygous abnormalities. Now we have two abnormal guys facing each other on complement chromosomes, okay? It's going to be a lot stronger, more complete, more uniform, appear earlier in life, quicker in life, and it's usually going to be to inherited mutations, very, very rarely acquired mutations. And in this case, the proteins will show a loss of function. Remember, with this guy over here, we said it's a reduced production or inactive, but in this one, it's a loss of function. So when we talk about the inborn errors of metabolism, we're probably talking about autosomal recessive disease. When we talk about a childhood genetic disease that's apparent in kids, newborns, we're probably talking about autosomal recessive. And if you thought this was a big list that kind of blew your mind, I'm going to give you another big list of these, and technically it's like much, much more common than the autosomal dominance. Okay, and here's part of the list. I didn't want to really blow your mind. I don't expect you to memorize this because it would be crazy. But what do all of these diseases generally share in common? Like cystic fibrosis, sickle cell disease, not the trait, phenylketonuria, the various complex thalassemias, galactosemia, Ehlers-Danlos, which we mentioned. We talked about abnormal collagen, and the huge, huge, huge list of lysosomal storage diseases, which we're going to spend a lot of time going through. Because remember, lysosomes are nothing but bag of enzymes. And so if you have an abnormal gene due to an autosomal recessive situation, and the enzyme doesn't work, okay, then the substrate that it acts on is going to build up. And these are things that might cause storage problems inside of cells. Alpha-1 antitrypsin, we'll talk about that with pulmonary and liver disease. Certain type of liver disease called Wilson's disease, and glycogen storage. Some of these things we'll go into right now. But I would say if you were told that somebody has a genetic disease, it's probably more likely it's autosomal recessive because the list is much, much greater than the autosomal dominant. And here's the pedigree. Okay? It could skip generations, whereas the autosomal dominant usually does not skip generations. And why is that? Because it's recessive. It's homozygous. All it takes is any one to produce the disease, and you need both of them. Okay, I'm sorry. I think I made a verbal typo there. The autosomal recessive pedigree skips generations simply because you need both abnormal alleles. And the chance of that happening is not as great as if it was autosomal dominant. I hope that makes sense. Okay. Now, the third type of classical Mendelian inheritance pattern is the sex-linked. Okay? And when we talked about the autosomal dominant and autosomal recessive, we talked about alleles and hetero versus homozygous, which means you need chromosomes which are paired, okay? Well, the X chromosome is not paired, okay? They usually say the X and the Y together, but the Y is not the complement or the homologue to the X. So obviously, sex-linked diseases are present when you have a defect in the X chromosome. And it doesn't matter what the Y is. So it's only in males, isn't it? Okay? So if you have a mutation in the X chromosome and there's no complement, it's going to be only in males because there's not going to be another X present. Okay? And if you pass that disease onto a daughter, that daughter is only going to be a carrier and will not have the disease, okay? So technically speaking, the concept of heterozygous versus homozygous or dominant versus recessive doesn't really have much of a meaning here. However, you'll very often see in the literature when they talk about a sex-linked disease that they'll say it's sex-linked dominant or sex-linked recessive. I really don't think that that's a good way of describing it, but it often is done by convention. So in sex-linked diseases, only in males, and if the daughter has the X chromosome that has a defect, then she's only going to be a carrier. Okay, so here is a list of some of the classical, common sex-linked diseases. You know, when we talked about Jerry's kids, which were generally the Duchenne and the Becker muscular dystrophies, that was sex-linked. So most of Jerry's kids with muscular dystrophy were males. Okay, classical hemophilia A and B due to specific factor deficiencies. A disease called G6 or glucose 6-phosphate dehydrogenase deficiency, okay, producing a hematologic abnormality, a sensitivity that might result in a hemolytic anemia. That's only in males. Baby born without any gamma globulin, more likely is going to be a male. Another sort of rare disease called Wiskott-Aldrich, diabetes insipidus, okay, not mellitus, but insipidus. Another type of metabolic problem with gout or uric acid called Leishmanian. And another syndrome, which we'll talk about a little bit later, Fragile X. These are all sex-linked. In fact, when we come a little bit later and take a look at the actual map of the X chromosome, we could show exactly, what arm, what band, what subband, what region that there is the defect on that would produce these chromosomes. So you could map out the X chromosome and say, agammaglobulinemia is going to be due to a defect here, and so on and so forth. And here's a sex link, and of course, it's only in the blocks, which are the boys. And it's only males, and it doesn't matter whether it skips generations or not, because it's going to be only in the males. Okay, theoretically now let's go back to the smallest level of mutation, the so-called single gene disorder. okay? Many, if not most of them, are enzyme defects. Why? Because genes code for proteins, and many proteins are enzymes. Okay, so this is probably the easiest concept to understand. If you have a defect of a gene that codes for an enzyme, that enzyme's not going to work. Okay, and the substance or substrate of which it acts upon is going to accumulate, and it may accumulate within the cell. It may kill the cell. It may cause the cell to be gigantic simply because of the accumulation of substrate due to the enzyme defect. And of course, there's not going to be any product because the enzyme doesn't work, okay? Or it may fail to inactivate a protein, okay, which also can cause cell damage. Now, let's say that that protein is not technically an enzyme, but it's a protein that carries or receives a substance. Well, now, if you have a defect in a protein that carries cholesterol, for example, you're not going to be able to process cholesterol normally the way it's processed in the liver, and you may have a buildup of it, and that buildup may be in macrophages, okay? So when we talk about foam cells or cholesterol macrophages with atherosclerosis, because the receptor protein for the cholesterol has a defect, now you can understand the nature of familial hypercholesterolemia. The gene might code for a protein which is a structural protein. You know, elastic fibers, collagen fibers. Okay, these are structural proteins. And if you have, for example, we'll give you a couple of examples. There's a disease called Marfan syndrome, in which the ultimate mutation is in a certain part of an elastic fiber called fibrillin. And if you can't make fibrillin properly, then you can't make elastic tissue properly, and the elastic tissue will be defective. Well, where do we have elastic fibers? Where do we have elastic tissue? Hey, we have them in our aorta in the so-called elastic arteries, don't we? And therefore, it might happen where these people might get problems with their aorta, like aneurysms. And we also have already mentioned the Ehlers-Danlos syndrome due to several different genetic mutations producing several different types of abnormal collagen. Well, if collagen is a substance which basically gives you fibrous tissue to firm up an area of your body that needs firmness, and now you're making abnormal collagen through a protein defect due to a gene defect, okay, your skin and other areas like your bones and other places that have collagen, which is basically every place in your body that has connective tissue, is not going to be firm. It's going to be rubbery, okay? People with hyperelastic skin are the classical presentations of various forms of Ehlers-Danlos. I have to tell you a story about one of our famous rheumatology professors. He actually had a class that I attended, and he asked everybody in the classroom if they are good dancers or good acrobats. He says, chances are, if you could really, really stretch your joints and flip your bodies, very, very easily, there's probably a good chance you probably have some form of Ehlers-Danlos syndrome. People that have won gold medals in gymnastics had a very, very good chance of having this disease. Now remember, enzymes can also protect cells. So if you have an enzyme defect that, for example, a G6PD, glucose 6-phosphate dehydrogenase defect, that's going to make certain cells more sensitive to drug actions. And the classical example of that always is primaquine sensitivity to red blood cells if you have a G6PD deficiency. Okay, here's a structural protein. So let's go into a couple of structural protein genetic diseases. Marfan syndrome, which results in abnormal elastic fibers because one of the components is a microfibril, which is partly made by fibrillin 1, even though there's a fibrillin 2 and 3. If you have an abnormal fibrillin 1, you're going to have abnormal microfibril, and it basically coats the elastin, which is not a fiber, but it's more of an amorphous substance. And that fiber, the elastic fiber, is going to be defective. And classical presentation of these patients is that they're tall, they have problems with their lens of their eye, but think about it. If you have a problem with elastic tissue, we have these things called elastic arteries, of which the aorta is the biggest and probably the most abundant one. So I actually had a medical student that had aortic arch aneurysm. He was very tall. He had Marfan syndrome. And by the way, he also was exceptionally brilliant as well. I'm not going to mention his name. It might embarrass him. Now, in the so-called hyperelastic syndromes, which could either have an autosomal dominant or autosomal recessive expression, there's at least 6 different types. Yeah, maybe by the time this lecture is over, there'll be 7. They have hypermobility of soft tissue, skins, joints. They can have a kyphoscoliosis, spine deformity, arthritic problems. But basically, if you take your skin and you pinch it and you bring up a little bump of tissue, people with Ehlers-Danlos classically have more elastic skin or more hyperextensible joints because of their abnormal collagen. Okay, remember we said there's about 18 different types of collagen, and several of them are involved in various forms of Ehlers-Danlos syndromes or diseases. Now here is the classical example of a receptor protein defect. You can have, not only does atherosclerosis run in the family, but there is a specific genetic disease called familial hypercholesterolemia. And it's because of a defect in the low-density lipoprotein receptor. Now, if the receptor transports cholesterol across a liver cell to be normally metabolized, and the transport protein is defective or absent, the cholesterol builds up in the blood. Hypercholesterolemia, that's why it's called hypercholesterolemia. And as a result, because it can't be processed by the liver normally, it's picked up by the macrophages, okay? Macrophages in the blood circulation are called monocytes, but monocytes in tissue are called macrophages. And with this buildup of cholesterol in the blood and the body, it basically has the macrophages swallowing your cholesterol. And as a result, they become foamy, they become fatty. Because remember, fats look foamy and washed out, and they become enlarged as well. And now you know why macrophages are foamy, because they are swallowing up excessive amounts of cholesterol buildup in this disease, because the cholesterol cannot be transported by the LDL receptor across the liver like it should normally be. Now, we're going to come into a big category of diseases now. And I don't know, don't freak out, because there's going to be a pretty good sized list of the so-called common enzyme deficiencies, of which the so-called lysosomal storage diseases are the biggest group, LSD. So when you think of an enzyme deficiency, think that probably the majority of them are LSDs, lysosomal storage diseases. Because you remember, lysosomes are bags of enzymes in cells, and in some cells like neutrophils, they're just loaded with them, but almost every cell has some type of lysosome, which will result in various types of digestive enzymes to deal with substances in cells. So, the concept, once again, is very simple. If you have an enzyme deficiency, you can't process or break down the substrate. And as a result, you cannot produce the product either. So what's the harm here? The harm is that if you can't process the substrate in the cell, it builds up. And it could build up to harm the cell, to kill the cell, to make the cell a lot larger. And this is the whole concept behind the enzyme deficiencies caused by specific gene defects which code for these enzymes, or perhaps polypeptide portions of the enzymes. And the largest category are the lysosomal storage diseases. Well, I want you to take a big breath right now, and so will I, because we're going to run through a list of them. Okay? And once again, I don't expect you to understand every single thing that goes on with everyone, but I think it's worth enumerating what the 7 or 8 or 9 or 10 most common lysosomal storage diseases, their name, and in every case we're going to be talking about an enzyme which is absent and can't process the substrate, so the substrate builds up. Okay? If you can't process glycogen, you're going to have storage diseases of glycogen in the places where glycogen normally are stored. You know, like liver and skeletal muscle and cardiac muscle. That's where a lot of your glycogen is. If your enzymes can't process gangliosides, okay, or sphingolipids, then you're going to have a buildup of this substance. And if these substances are common in the brain, you might wind up having brain disease. And remember, almost all of the lysosomal storage diseases and even enzyme deficiencies are autosomal recessive. So for the most part, these are going to be present early. These are many of them childhood, and often fatal childhood diseases as well. If you can't process a sulfatide, of which there are other chemical divisions of it, then you're going to have one of these sulfatidoses. Some of these have specific names. Some of them even have poster children as well, okay? If you can't process, break down your mucopolysaccharides, you're going to have a buildup of it. Another category of biochemicals, the mucolipids, if they can't be processed, broken down by the enzymes that break them down, they are going to build up, cause damage, and depending on where they normally are the most abundant, will possibly cause damage to that particular organ. Now, if that wasn't enough to blow your mind, I'll also make a quick mention of the same principle going on with fucosides, mannosides, aspartyl-glycosamine, which can't break down, so it builds up in the urine. A disease called Wolman disease, and if you have the absence of an enzyme called acid phosphate tase, an acid phosphate deficiency is also considered in these lysosomal storage diseases. The one thing I do expect you to know, is that if you see any of these names anywhere, not just on an exam, perhaps you heard of a patient from one of your pediatric friends, that these are all genetic lysosomal storage disease enzyme deficiencies. Well, here's glycogen. There's at least 10 different types of glycogen storage diseases, depending on where in the metabolism of glycogen things are broken down into glucose, okay? You might hear the name Pompe, von Gierke, McArdle. They're all different clinical presentations, but the common denominator is that Glycogen, as you know, is normally stored in liver. If you do electron microscopy, you can see a lot of glycogen granules in the liver, skeletal muscle, or the other striated muscle that we call cardiac muscle. And if the glycogen builds up, then normally these fibers, like you see here, might look washed out because the glycogen is the majority of the cell and it dissolves in the processing. So sometimes it's mistaken for fat because it's a clear space. But remember, not only do fats dissolve in processing, but technically water-soluble carbohydrates can do it as well. Here's another situation in which we have an organ. At this point, I know this is muscle, so let me see if I could guess what this is. Oh, I really don't know, but you see a bunch of foamy cells, and some of them are washed out. And up here in this one, I don't know if I want to. This is probably liver, and this could be liver, and you could see that, like with fat, which is washed out, so is the glycogen. Okay. You may have heard of Tay-Sachs disease. It's generally a fatal disease. Tay-Sachs is a disease present very, very highly in the Jewish population because 1 out of 30 Ashkenazi Jews are carriers. Okay? So when those carriers produce an autosomal recessive situation, you now have lack of hexose aminidase A. Okay? Now, hexose aminidase A, you would imagine if it's gone or deficient, it can't process the type of chemical compound we refer to as gangliosides. And therefore, the gangliosides accumulate. Now, where do you think gangliosides are common in chemically? Central nervous system. So this disease presents very often early after birth, like a few months, and unfortunately, it's usually fatal by a couple of years. We'll say up here the statistics are results in death by the age of 4. Okay, very serious disease. Why do you see this neuron have a big foamy dilated cytoplasmic blob? I'll tell you why. Because it's building up ganglioside, okay? Gangliosides are also a type of phospholipid. This is in the central nervous system, and a neuron of the central nervous system. You know, and my son is an ophthalmologist, and I've asked him if he's ever seen clinically what they call a cherry red spot, okay, in the macula. And he said, yes, he's seen a couple, okay. So this is probably in a child that will statistically not live very long. Sulfatides. Sulfatides are also chemical compounds present in CNS, okay, and other organs. But if they cannot be processed, okay, they could produce diseases which classically, generically were named things like Crab disease, Fabry disease, Gaucher disease, Niemann-Pick disease, okay? And once again, the sulfatide buildup, if you break them down there in categories of cerebrosides, so you know that's probably in the brain, sphingomyelin, which you probably know is in myelin tissue. These are the accumulations because they lack the enzyme. And I think we're going to actually go into a couple of specific ones, like Niemann-Pick disease we'll start out with. Once again, unfortunately, the gene runs high in Ashkenazi Jews. If you have a defect in an enzyme which processes the sphingomyelin, and yeah, as you might guess, there's several different types of disease, but in every case, you have a buildup of sphingomyelin, okay, and it builds up in macrophages, okay? And this one looks like it's probably liver, but it could also be in cell membranes like myelin sheath and nerve cell axons. So once again, this is a very serious disease. And like Tay-Sachs disease, or what they call TS, it's often fatal in early life. With organomegaly, and especially in the organs, which have a lot of macrophages like spleen, liver, okay, and buildup of these foamy cells in the central nervous system too. Here's Gaucher disease. Generally not quite as horrible as the last couple we talked about, but in Gaucher's disease, the enzyme deficiency specifically is called glucocerebrosidase, okay? And if you're thinking, well, it must be something like a carbohydrate and maybe it's in the brain. Yeah, but it's a lot of other places too. And in Gaucher's disease, the primary buildup are in macrophages, okay? There's a lot of macrophages in your liver, and there's a lot of macrophages in your spleen, your lymph nodes, your bone marrow. And if you are looking at a bone marrow or examining a bone marrow for the presence of some hematologic abnormality, and you see a lot of these foamy cells, you could maybe suspect that this is Gaucher's disease. And I have to tell you another little story again. When I was a resident, we had a brilliant hematopathologist, and we're just looking at bone marrows every day to look for abnormalities, and he saw little funny cells here. And the patient did not have the diagnosis of Gaucher's disease. They were there for some other problem, maybe an anemia or something like that. So he goes up to the chart and the patient, and he does the examination, and sure enough, that patient had Gaucher's disease and never even knew it until we just happened to be looking at the bone marrow. Okay, here's another chemical compound called mucopolysaccharides. And as you guess, there's a muco type component and a saccharide component, okay? And the two classical mucopolysaccharidoses, which result in the inability to process mucopolysaccharides, and one of the mucopolysaccharides is called dermatan, and another type of specific mucopolysaccharide is called heparan. So there's basically a couple of main types of mucopolysaccharidoses, or lack of an enzyme to process these. And one of them is called Hurler disease, and one of them is called Hunter's disease. And Hurler disease, probably I would guess, was the first one discovered, so that would be mucopolysaccharidosis type 1. And Hunter disease, probably later, is type 2. The way I remember it is it's not in alphabetical order. So, and actually a Hunter comes before Hurler alphabetically, but the Hunter disease is actually the second one, or mucopolysaccharidosis type 2. So when you have a buildup of these compounds, I would say the one way they present clinically, and once again, usually as kids, they're rather, I don't know, I don't like to use the word, but I actually got this out of a textbook, and I almost really don't want to use the word myself, because these are kids that are, seriously ill. Coarse facial features. So if you agree that these kids, we're all beautiful kids, but they have kind of bold or coarse facial features. They have problems with their corneas, they cloud. They have problems with their joints. And of course, the big problem is mental retardation, because the buildup of dermatan sulfate and heparan sulfate in type 1 and type 2, or Hurler and Hunter respectively. And not only that it builds up, but they also can be excreted in the urine because of excessive buildup as well. And here are a couple of poster children, okay? This is a very serious disease that has a lot of people in it. Okay, if you think we're done with the long laundry list of classical enzyme lysosomal storage diseases. I want to do an honorable mention for just a few more, if you'll bear with me, and then we'll have a break and have some nice music, and you could say, wow, I'm glad we're done with that part, because then it'll get more clinical and more easy and more interesting in the second half. So, what would you think a fucosidosis would be? Well, I think it would be a buildup of fucose because of the enzyme which processes it or breaks it down, called alpha-1 fucosidase. Okay, and deficiency of that causes fucosidosis. Same thing with mannose. Mannose is a carbohydrate, a sugar, and if you can't process it, it builds up, and it's the same general principle as the fucosidosis. If you have now in your urine, aspartyl glucosamine, maybe aspartyl glucosamine can't be processed either. And here I have the name of the specific enzyme which is absent. It's called N-aspartyl beta glucosamidase. And if that's absent, that carbohydrate, I think it's probably probably protein is partly as well, builds up in the lysosomes as well. Wolman's disease is the common name, okay? It's basically a buildup of cholesterol and triglycerides. Why? Because you have an acid lipase deficiency. So if you can't break down fats, they build up. Finally, an acid phosphatase deficiency. I'm sure you can probably predict what I'm going to say by now. Because of the absence of enzyme, is going to be a buildup of phosphate esters chemically. Okay, you know what? Thanks for bearing with me. We're about halfway done altogether. But we'll go into, I normally probably would do this now, but I feel sorry for you for going through that long laundry list. And actually, L-captonuria is not exactly in this category, but we'll talk about it as an enzyme deficiency after our break. So let's hear 3 nice songs. And I'm not going to wear the mask again. Maybe you could look at Rosa for a while to rest your eyes. Or maybe, let's see. Maybe we'll put on the webcam too. No, I think I'm going to have you look at Rosa. She's very easy to look at. And we'll play 3 more songs. See you in about 10 minutes. Boo!
Like the dolphin who guides you, to bring us beside you, to light up the darkness and show us the way. For though we are strangers in your silent world, to live on the land we must learn from the sea. the wind swell, joyful and loving in letting it be. I calypso, the places you've been to, things that you've shown us, the stories you tell. I calypso, I sing to your spirit, the men who have served you so long and so well. I calypso, the places you've been to, the things that you've shown us, the stories you tell. I calypso, I sing to your spirit, the men who have served you so long and so well. Deep down in Louisiana, close to New Orleans, way back up in the woods among the evergreens, there stood a log cabin made of earth and wood, where lived a country boy named Johnny B. Good, who never ever learned to read or write so well, but he could play a guitar just like a ringing a bell. Go, 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 Johnny, go, 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 Johnny, go, 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 Johnny, go, 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 Johnny, go, go. Johnny B. Good. He used to carry his guitar in a gunny sack, go sit beneath the tree by the railroad track, bowling and everything sitting in the shade, strumming with the rhythm that the drivers made. People passing by, they would stop and say, oh my, but that little country boy can play. Go, 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 Johnny, go, 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 Johnny, go, 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 Johnny, go, go. Go, Johnny, go, go. Johnny be good. His mother told him someday you will be a man, and you will be the leader of a big old band. Many people coming from miles around to hear you play your music when the sun go down. Maybe someday your name will be in lights saying, Johnny be good tonight. Go, 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 Johnny, go. 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 Go, Johnny be good. when I am down and oh my soul so weary, when troubles come and my heart burden be, then I am still and wait here in the silence until you come and sit a while with me. You raise me up so I can stand on mountains. You raise me up to walk on stormy seas. I am strong when I am on your shoulders. You raise me up to more than I can be. You raise me up so I can stand on mountains. You raise me up to walk on stormy seas. I am strong when I am on your shoulders. You raise me up to more than I can be. You raise me up so I can stand on mountains. You raise me up to walk on stormy seas. I am strong when I am on your shoulders. Raise me up to more than I can be. You raise me up so I can stand on mountains. You raise me up to walk on stormy seas. I am strong when I am on your shoulders. You raise me up to more than I can be. You raise me up to more than I can
Well, those were our three songs, and now we're in the second half. And usually, between the first and the second half, when I filter my coffee in the next room, I usually think of things I should have said and want to add something that I've already said to. That last song we played, You Raised Me Up, was one of the most beautiful and spiritual songs I've ever heard. It just always gives me goosebumps. There's one that makes me cry, but that's not it. Okay. Very often, I'm sure you will agree in your life, you realize that you might have a job to do that you think you're just not capable of doing. Okay? Like teaching an entire medical school course twice a week, for 12 years. I never thought I was capable of that. But this spiritual song, and remember, it's a spiritual song, it's not a religious song. It's not Christian, it's not Muslim, it's not Hebrew, it's not Hindu, okay? It's a spiritual song. And I want to say just one thing. When you realize that you have done something that you were not capable of, especially something good, I think you know, and I don't have to give the name, I think you know who was really behind it. Okay, let's go into our second half. Here we go. Let's see if our PowerPoints are still up. Okay, just finishing off a little bit on this concept of lysosomal storage diseases. This is not a lysosomal storage disease. This is one of the first enzyme deficiency diseases to be described. And then once again, it's the same concept, however, it's just not lysosomal. You have a substance in your body, homogentisic acid. Okay, ultimately, chemically, you could look it up. It is related to tyrosine, the amino acid, and phenylalanine. If you remember, tyrosine is also an amino acid involved in some of the pigments, like melanin, for example. So let's say theoretically, due to a gene defect, you had a defect or absence of homogentisic acid oxidase. That means that this substance then, homogentisic acid, which has rich in tyrosine, the same amino acid involved in pigments, would then build up as black deposits in various parts of the body. And also, possibly, if it was high enough, to be excreted in the urine as well, because it's not metabolized. So patients with alkaptonuria may have black urine. They may have black nails, or basically what you're seeing in the nail bed as well. And they may have increased depositions of black substance into the skin. And also, it's something that is present in cartilage, so you may see that black cartilage. And I know what you're thinking. You're thinking, how can you see black cartilage, you know? Well, don't forget, there's only a little flap of skin over your ear, which is mostly external ear, which is mostly cartilage. So you can see black ear cartilage underneath the skin. And of course, cartilage being a very important component of bones and joints, okay? Patients can have severe arthritis. Here's the black urine. Here's the black cartilage in the ear. Here's the black nails and nail beds, fingers and nails, especially the big toes, where the nails are the thickest. And microscopically, the substance looks like it's been building up in the dermis. There's a deposit, there is that. You could almost count them. There's probably 30 or 40 of them in this field. Some are big and dark, and some are not quite so big and dark. This is homogentisic oxidase in alkaptonuria. Classical genetic disease, which we cannot escape, is neurofibromatosis. What is neurofibromatosis? Well, it's a disease in which patients have a lot of bumps all over their skin, perhaps hideous even, called neurofibromas. Okay? And they also have a lot of areas of their skin that's pigmented, you know, like coffee, like the coffee that I show you every webinar, that cafe au lait spot it's called. So there are two types of neurofibromatosis, genetic disease, producing the buildup of these subcutaneous bumps, like here and here. They could be in the face. And these little pigmented spots, cafe au lait spots. And the pigmented spots in the eyes are called Lish nodules. And I don't know if you'll ever be lucky enough in your career. I haven't been lucky enough to see a Lish nodule in real life, but my son has told me he's seen a lot of them. Okay, these are buildup of pigmented areas. Why? It's because the enzyme deficiency basically involves all neural crest cells, some of which are melanocytes, if you remember, Schwann cells. So you could build up these little neural tumors in the skin, also in areas where there's nerves, like in your spine and your peripheral nerves, okay, in your brain as well. And there's another type of neurofibromatosis, number 2, in which the primary clinical expression are acoustic neuromas or acoustic neurofibromas. And that is basically tumors of the acoustic nerve, inside the brain at the CPA, or what they call the cerebellopontine angle. Okay, so here's neurofibrosis 1. Bumps and coffee spots, and if you're lucky enough, Lisch nodules. Okay, but in neurofibrosis number 2, not only can you see often as the clinical expression acoustic neuromas, and this is an area where you might get acoustic neuroma, and I got news for you. Often they're bilateral as well. So I got to give you a tip, and you may know it already. If you see a patient and he's got some type of hearing problem, you wind up getting a MRI or CT, whatever, and you see a couple of bilateral acoustic neuromas, you can guess that's probably a neurofibromatosis type 2 patient. And also meningiomas as well, okay? Meningiomas are going to be basically fibrous type nodules that you would see associated mostly with the dural meninges. I think you could see one here. I think maybe you could see one here. Okay, so neurofibromatosis 1, skin bumps, fibromas, perhaps internally as well. Cafe au lait, neurofibromatosis 2, acoustic neuromas, and often multiple meningiomas, and often bilateral neuromas, okay? Acoustic neuromas. Well, up until now, we've been talking about single gene mutations. And you're probably wondering, are there any diseases which involve multiple genes? And even though you could understand the concept of a multiple gene defect causing a disease, it's usually called multifactorial rather than just multigenic. And very, very often, these specific genes, especially if there's more than 1 or 2 or 3, are not clearly identified. So when you have a disease that's called multifactorial or multigenic, you're probably not going to get the name of a specific gene. Now, this is something that I coined myself. It's called the soil theory. If multiple genes, or let's say your genome, determines your protoplasm, okay, your tissues, your organs, then you're going to have a soil or a protoplasm, which is very similar to what your parents have, to what your children have. The closer the familial relationship, the more likely you are to see a disease. So why is your hair a certain color? Why is your eye or skin or your height or intelligence or even diabetes type 2? What would you say is present in all of these situations or diseases? Number one is it's not determined by one gene. And also, it's a measure of something that is not either like an on or an off disease. It's usually measures something that is a scalar type situation. I think I'll have to define that a little bit more precisely. The features of multifactorial inheritance. And remember, it's not just multifactorial diseases, things like skin color, eye color, okay? It's a continuous trait. In other words, height. You could be 6'1", you could be 5'1", or anywhere in between. This is a continuous trait rather than a discontinuous trait. In other words, a disease like diabetes 1, which is either present or not present, okay? These are scalar type of situations. So, even though when your patients come in and you do a family history, especially if they have a specific disease, you always inquire about if anybody else in the family has it. Or you also inquire about diseases that they don't have that might be in the family, okay? So how do you know if somebody has a situation or a feature of a multifactorial inheritance? Well, first of all, take your first degree relatives, your mother, your father, your child, your daughter, your son. That's a first degree relative. If you have a feature or a disease of multifactorial inheritance, there's going to be at least a 5% chance of the relatives also having it. Okay, now remember, some of these diseases or situations can be very rare, like 1 in a million. But if you have a disease that is generally regarded as multifactorial without naming specific genes, that 5% seems pretty big. Now, I know what you're thinking. You're thinking, well, if you have a identical twin, then that twin has to have it because he has exactly the same soil. He has exactly the same genome. But it's definitely a lot bigger than 5%, but it's not 100%. Okay. Now, if you have relatives that have it, first degree relatives, then there's a lot more than a 5% chance that other relatives will have it too. So it's all a probability thing. And here, let's go into a little bit of a list here. These are the so-called multifactorial disorders. And I know by the time I'm done rattling them off, like cleft lip, cleft palate, congenital heart diseases, coronary heart disease. Oh my God, doesn't everybody have that? Hypertension, oh my God, that's probably half of everybody that walks into an internist's office. Gout, diabetes, so common, pyloric stenosis. This is a list, but don't you think, more practically speaking, and I don't want to minimize the importance of a multifactorial disorder, but don't you think that probably perhaps many, or perhaps most diseases are sort of multifactorial? Because most diseases occur in patients that have gazillions of genes, and so do their first degree relatives. Probably very similar genes. Okay, we're done with that concept of multifactorial. And there's a list, and you can say, my God, that looks like it's probably every disease known to man over there. Let's talk about move from the one gene to the so-called multi-gene or multifactorial. And now let's talk about a whole chromosome. And karyotyping is the study of chromosomes, whole chromosomes and parts of whole chromosomes. And as you know, we all have 22 autosomes and 2 sex chromosomes. And if it's an X and a Y, you're a male. If it's an X and an X, you're a female. The common nomenclature for a male would be 46 XY, for a female, 46 XX. That's your conventional notation. Now, there are ways of actually looking at these chromosomes, even on a regular light microscopy with H&E during phases of mitosis. You could sometimes see almost entire chromosomes. But there's another stain, a common stain. It's not quite as accurate as these gene probes like FISH, but it's called Giemsa banding, a Giemsa stain. Giemsa is a stain that's used for a lot of things like bone marrows and blood cells, Giemsa variants. And on the basis of just staining chromosomes, especially at stages of mitoses where they're the most obviously visible, you could actually see 500 bands per haploid set. Isn't that amazing? Normally, when you look through a microscope, you see a little string and you don't get much further than that. But if you use Giemsa and you have a good microscope, you can see not only the entire chromosome, but where it splits. You could see the petite arm or the P arm. The P stands for petite. Or the Q arm, which is the longer arm because it's not petite. And this is basically karyotyping. This is, I think you could see right away, we got 22 chromosomes. We're going from the taller ones to the shortest ones. So the tallest ones are A, and then the next tallest group is B, and then C, D, all the way down to G, which are the shortest ones, in which you could barely see the differentiation between the two arms. And then finally, after you got those 22 or 44 chromosomes, you're going to have either X and a Y or X and an X, okay? Normal, this is a normal male, okay? So you have 22 autosomes, and you move into the A group, of which there's 3, and then the B group has 2. And then the C group looks like it's pretty big. It looks like it has about 7. And then all the way down to the shortest one, which is 22, and then the X or the Y. Now, did you notice something funny about these chromosomes? Not only do you see the little strings and perhaps the centromere portion, but you could see little dark and light areas. So now we can not only see the entire chromosome and not only see the centromere and the part of the centromere that's short or petite above the centromere and the part that's longer or Q, but you can see these little bands. So not only are we looking at chromosomes and P or Q arms, but we're looking at regions of the arm. And then within the regions, we're looking at something called bands. And remember, we said that 500 different bands are recognizable in a genome normally. And furthermore, you can also go into the subbands. You're probably thinking, oh my God, you're almost going into the DNA molecules. Of course not, because we're talking about a genome of, 3 billion base pairs. And up here we're talking about visible of only about 500 regions, technically, at best. And you number them from the centromere, and you continue away from the centromere. So here's the centromere. Here is the shorter portion called the P, because it's petite. And then here's the longer one, which is called Q, which is not petite. And then here is the region within the P. There's a couple of them. This happens to be the X chromosome. And there's a couple of regions within the Q. And then within the region, there's 2 bands here, 1 band here. And then you even have as many as 3 sub-bands. Now remember, I told you that at some point in time, we are going to look at an individual chromosome. In this case, it's the X one. And you could take little regions of that chromosome. In other words, not just an arm or a region or a band, but even a sub-band, a very tiny portion, perhaps at a band or sub-band level, and actually map out the various X-linked diseases. Like here's Leishmanian. Remember that was part of our list of X-linked diseases. Here's Fragile X. Here's hemophilia. Here's G6PD. Menkes disease, testicular feminization. These are all male diseases. Now let's go even deeper, because now we're getting into the fancy stuff. This is just a stain. This is a Giemsa band or subband, okay? But now let's put in some probes. And in pathology and medicine, there's a technique called FISH. And the F stands for fluorescent. And then in the ISH is in situ hybridization. These are the little gene probes. These are little DNA fragments, perhaps 10,000 base pairs on the average. It could be bigger. But they are fluorescently labeled. And if they correspond, or they to the DNA molecule, okay, you're going to see a little fluorescent buzz. And if they don't, you won't see it. So that's basically the process. It's very, very complex, but think about it. You're putting in about a fragment of DNA, maybe 10,000 base pairs, and it's fluorescently labeled, so you can see whether it binds or doesn't bind to its complement. So here are some reasons why you might want to do FISH. maybe you're suspecting there's a part of a chromosome where that's deleted, but you can't really tell by games of banding or any other way. So that's a really good reason. So if you have a disease and you could pick up a subtle, very tiny microdeletion by fish, you see the lack or the presence of that little fluorescent dot, then you could suspect it's a microdeletion on the string that's smaller than you could normally see. Or a complex translocation, where you have one part of a chromosome crossing off to another one, okay? It could be simple or it could be complex. And also telomere alterations. Now, if you remember, the telomeres are the ends of the chromosomes. And if you have an alteration or a problem with a telomere, you're going to have an alteration or a problem of what telomeres do. And you might remember that telomeres determine the number of mitoses a cell can have during its life. So if you have a telomere problem, this cell may not be limited into the number of lives or mitoses that it has. In other words, it could multiply forever like many tumor cells do, correct? Here's a fish study which identifies a chromosome 20, and in every one you can see there's 3 little areas, so it probably has 3 chromosomes, number 20. That would be a trisomy. Rather than having 2 chromosome 20, it has 3. Here's one that shows a very subtle and small deletion in chromosome 22, and as a result, you see a fluorescent area that is present there, okay? I just throw this in. This was also a picture we had at the beginning of our PowerPoints, and it's beautiful. That's why I threw it in. It just looks pretty. I'm not going to say anything about it. And it's not really much used in medicine, but there's a way to false color things. Like with electron microscopy, we could give certain types of areas false colors. So wouldn't it be cool if you could actually, do a karyotype study and pretty much label almost every chromosome a different color? Isn't that cool? That's spectral karyotyping. It follows the spectrum of the rainbow. How do you like that? So let's get into now actual diseases or disorders, which are due to whole chromosomes or parts of whole chromosomes, more than just gene mutations or multi-genes. And here are some concepts we have to deal with. If you have an exact multiple of 23, like 46, for example, then you are euploid, because a euploid cell has 23 times 2 chromosomes. If it doesn't have an exact multiple of 23, it's not euploid, or what they call aneuploid. If you have a missing chromosome entirely, that's a monosomy. And that could be of either the 22 autosomes or a sex chromosome, which means X or Y. If you have an extra chromosome, trisomy rather than 2, then that would be called a trisomy. Could a chromosome have a deletion in it? Yes. Could it break? Yes. But I want you to remember, rather than just looking at this list, that if you have, once again, your concept of a string, okay, you got a string in your hand. Maybe you took off your shoelace, or maybe you took off the back of my pirate mask, and you're looking at it like a little string. Anything you could do with that string, tie it in a knot, cut it up, make it into a circle, split it in a funny way, take a portion and invert it. Anything you could do with that string technically would be possible with the chromosome. And I'm going to give you a list to prove that, even though some of them are very, very rarely seen. So these are cytogenetic disorders. So look, there's your string, okay, and you translocated one chromosome to the other. That's a translocation. You probably knew that. Okay, Could you translate just the big portion rather than the little portion? Yeah, then you wind up going to have a chromosome that's much longer than it should be because the translocation, spared the long arms, and the short arm fragments, they say, is lost. I don't understand it, but that's what my little chart says. Now, you know how chromosomes should normally divide and separate at the centromere, but what if they separate along P and P and Q and Q rather than P and Q, P and Q? That's called an isochromosome, and that's possible as well. Remember, anything you could imagine with a string. What if you took a string and just chopped out part of it? That's a deletion. What if you took the string, a portion of either the P or the Q arm, and you inverted it? That's called an inversion. Okay, it could either be on one side of the centromere or both sides. Be paracentric or pericentric. Finally, probably the easiest thing you could imagine to do with the string is to take it and make it into a circle rather than a linear structure. And yes, you can have ring chromosomes as well. You can have these diseases, you could have these in tumors. And for those of you who have already seen a lot of tumors microscopically, we're going to be doing that a lot in the future. You're going to see chromosomes that, can look like, Justin Bieber. Or just about anything is possible for that chromosome, if you remember the stringed concept. Here are the common autosomal diseases. Trisomy 21 is not only the most common trisomy, but it's the most common cause of mental retardation, probably in the world. Okay? If you have an extra chromosome 8 or 9 or 13, okay, this is called Patau syndrome. I hope I'm pronouncing it right. If you have an extra 18, that's an Edwards. You could have an extra 22. These are generally very, very serious diseases, and most of the other numbers are basically incompatible with life. That's why they're not even seen other than 8, 9, 13, 18, 22, and the most common one, 21, also called Down syndrome, also formerly called mongoloids. Okay, that was kind of a politically incorrect term. So now it's most often just called Down syndrome or trisomy 21 if you want to be a little more scientific. Or another common cytogenetic disease is not an entire chromosome, but a deletion in parts of the 22q, which is the long arm, at the 11 band or subband, called 22q11.2. Now that disease goes by a wide variety of names, and we're going to go over it, and we're going to show you why it has a wide variety, because then you'll understand some of the clinical expressions. But overall, of all the crazy names that this syndrome is given, I like the word catch, C-A-T-C-H, the best, and we'll show you why. Or you could have cytogenetic diseases of sex chromosomes. Here's a man with an extra X chromosome. It's a trisomy. So rather than having XY, he has XXY. And that's true like about 90% of the time. But in other cases, he might have 2 additional X's. Okay? And I've seen those X's go up to, 4 and 5. So any man with an extra X chromosome, he's a man because he has a Y, is called a Klinefelter syndrome. The more X's you have, the more likelihood there is of a mental retardation. But in the usual run-of-the-mill XXY, there's no significant, or maybe I'll say no mental retardation. In a woman now, she's a woman because she doesn't have a Y. In fact, she doesn't even have another X. So O is not a ring chromosome. O implies that this is a woman with a monosomy. This is called Turner syndrome, often called XO. And that has a variety of classic clinical presentations as well. So here's your classical karyotype for Down syndrome. Probably the most often, by far, studied chromosomal disease. You have 3 A's, 2 B's, 7 C's, 3 D's, 3 E's, a couple of F's, 2 in the F, 2 in the G. But in the G, chromosome 21, one of the shortest chromosomes, has an extra chromosome. And then, of course, you know, this is a Down syndrome male rather than a Down syndrome female because they have a Y chromosome. So, why would somebody have an extra chromosome? Well, perhaps when you get to the stage of mitosis where the chromosomes separate, maybe in that particular area they didn't separate. So it's called non-disjunction, okay? Now, what if technically it could separate, but it separated too long at anaphase, you know, when they're separating? Then that's another technical explanation for trisomies, and specifically trisomy 21. It's the number 1 cause of mental retardation. It's related to maternal age. A woman that is in her, let's say, 40s or late 30s and beyond who's having a baby is probably her number 1 worry. The babies are at risk for some certain types of congenital heart diseases, acute leukemias, and narrowings or perhaps even complete strictures of parts of their gastrointestinal system. So trisomy kids, okay, don't live generally as long, and when they don't, it could be because of a serious heart defect and a leukemia or a GI obstruction. Now, you could probably ask, why did I put this stupid little comment at the bottom? Why are they the most lovable of God's children? Okay, well, the reason I did that is if you had one in your family as well, you'd probably say the same thing. Another thing I want to point out about Down syndrome or trisomy 21, and I don't think anybody else will ever tell you this, but there's just something, and someday I'll be able to explain it and understand it. But right now, I'm going to tell you, if you go to Google Images and you just go to Down syndrome and you see like 100 pictures of Down syndrome faces, once you see 1 or 2, you're going to remember that general look for the rest of your life. Now, there are certain diseases, you know, other chromosomal disorders, you know, like the Catch syndrome we talked about, which you'll never really instantly recognize one if you see one, but in Down syndrome you can. Okay, and I think this was a little link to a page that showed like a whole bunch of Down syndrome pics. And I guarantee you, even if you're not a pro, or even if you can't even recognize what shoe you put on properly in the morning, okay, if you see 1 or 2 Downs, you'll just know them for the rest of your life. Nobody else will tell you that, by the way. Here's another chromosome disorder, and we're going to call it Catch, but the only reason we're calling it Catch is because I can't remember 22q11.2 that well, okay? It's a deletion of that part of the long arm of chromosome 22, which is called maybe a band or a subband or a region in the band. And that's the part that basically is important in the development of heart, parathyroid, parts of the face, you know. So it has been given the name velocardial facial syndrome. Okay, it has been called DeGeorge syndrome because part of it is involved in the immune system. But I would like, and look, here's some other names here: conotruncal anomaly, congenital thymic aplasia. Okay, that's the DeGeorge part. So that's the fact that there could be a thymic hypoplasia or a very significant cellular immunity problem. But the reason why I'd like you to remember Catch, even probably though nobody else will, it's a mnemonic. And the C stands for cardiac anomaly. The A is an abnormal facies. It's not quite as diagnostic instantly as Downs, but it's an abnormal facies, and I will describe it. Thymic aplasia. So you think, oh, these got thymus problems. He's probably going to have problems with their T cells and their immunities. A cleft palate, and that's the facial portion of the term velocardiofacial. And hypocalcemia. Why? Because it also involves, that area also involves the development of the parathyroid gland. Okay, and if you don't have good parathyroid function, you're going to be hypocalcemic, obviously. Here's a couple of poster children. And once again, they're not as quite instantly diagnostic. But I will say one thing is that they all have really cute smiles. Now, there's a lot of people that have cute smiles. But in the velocardiofacial syndrome, when they smile a little bit, you're going to remember that smile. Okay? So let's move on now to the sex chromosome disorders, the major ones. A person with a sex chromosome disorder, whether it's classically a Klinefelter for a male or a Turner for a female, they often don't have these problems manifest until they reach puberty, when their sex organs mature. That's when it's usually discovered. And if it is associated with a mental retardation, that's usually dependent on the number of X chromosomes. The more X chromosomes you have in a sex chromosome disorder, the more likely you have to be retarded. Fortunately, about 90% of the time, it's only one X chromosome in which there's no significant mental retardation. Now, I get into my little speech because there's all this crazy stuff going on in the world. What is a man? What is a woman? What is a gender? You get all these different genders. I basically will tell you that if you have a Y chromosome, you're a male. Let's make it obvious, okay? Once I put a picture on Facebook, and I put down all these other crazy so-called genders, and I called them all, I think I called them all mental diseases or something like that, and I got kicked off of Facebook for a month. So, actually I've been kicked off of Facebook 22 times now, so, that was no big thing. This is the number one cause of male infertility. Klinefelter. It's a man with a Y, so he's a man, and he has an extra X or maybe 2 or 3 extra X's, but usually only one. XXY is the classical feature, like 82% of the time here. Hypogonadism, found at puberty, small testicles, small penis, usually not retarded. If you want to remember it in kind of a funny way, maybe I shouldn't say funny, they're tall, okay? So they have, and the tallness is usually in their legs. So they have long legs and short penises. How does that sound? And of course, the presenting thing is hypogonadism, so atrophic or barely palpable testes, let's say, at the time of puberty. Here's a Klinefelter guy. He's tall. He has a very tiny penis, but he has long legs. And, there's feminizing features, like some breast development or a female triangular type of pubic hair distribution, wider hips like women have. Okay, so this is a classical Klinefelter. Let's move on to the woman. Turner syndrome. She doesn't have another X. He only has an X. And of course, she doesn't have a Y either. Otherwise, she wouldn't be a woman. Okay. So 45X is the designation, the way you would call it. It doesn't have to be entirely every cell in the body. It could just be in certain cells or gonads, let's say. So the mosaics are very, very common. And often, it's not even the whole chromosome that's missing or just a part, but generally speaking, to make things simple, a woman does not have an entire or intact second X chromosome. The word you will always hear in describing her clinically is that she has kind of a webbed neck. And ovaries, I don't know if you've seen ovaries at surgery or at autopsy or at your anatomy table, but they're bumps. They're actually like little buttons. In this case, it's just kind of a streak, a little tiny, barely perceivable streak in the broad ligament, and there's really nothing that you could dissect out as a specific structure. They have edema of their hand, and all of these things are basically not life-threatening, but they do have certain types of congenital heart defects like coarctation of the aorta. Let's take a look and we could quit talking about it. There's your webbed neck or an extra fold of skin in the neck. There's your most feared consequence is constriction or coarctation of the aorta. They don't menstruate. They have rudimentary or what they call streak ovaries. And they might have a few extra brown spots. They have edema of the dorsum of their hand. Okay, and for a reason I don't understand, the nipples are a little bit further apart than they normally should be, but the breasts themselves don't develop very much. So there's probably a classical Turner syndrome over there. We're near the end. We just have a couple more things. But you have to talk about hermaphrodites. You know, there was a Greek god named Hermes, and he had a shield. Here's the shield of Hermes. That way you know it's a man. And then we had a Greek goddess named Aphrodite. Okay? And here's her, I'm sorry, here's Hermes' sword. I made a typo. And here's Aphrodite's shield. So hermaphrodite, you would think, would be somebody with both male and female features. Almost all of the people that you hear of that are called hermaphrodites, they do not have both testes and ovaries. They are really pseudo-hermaphrodites. So a pseudo-hermaphrodite male is somebody with testes, but he has female secondary characteristics. A female hermaphrodite is a female, XX, but she has a lot of male masculinizing features, okay? Now, if you could imagine that there would be a possibility of a person with ovaries and testes, and these are very, very rare. I don't think there could be more than probably 2 or 5 in the world. I don't know. It's very rare. I never seen one. You'll never see one. And very often, if you do, you could have ovaries on one side and testes on the other side. But remember, with all the craziness going on about, gender, kids waking up one morning and they're boys, but they want to pretend like they're girl genders or vice versa. This is craziness. But true sex is basically chromosomal sex, isn't it? Presence or absence of a Y chromosome. But you can also have gonadal sex, person with a penis, or gonads internally or externally, no matter what all the other things would be called male or female. Or if you remember from embryology, there's the Mullerian duct, which gives rise to large portions of the internal female genitalia. And there's the Wolffian duct, which gives rise to male ductal sex features. So there's a lot of different ways you can talk about sex, without talking dirty. And finally, at the end, there's a couple things left. We've all been talking about genetics diseases on the basis of Gregor Mendel, that famous monk that talked about inheritance patterns. However, I think it would not be fair if we didn't say that there are other types of genetic diseases which do not follow the classical Mendelian laws. And one of them is the Fragile X syndrome. Remember, this was the prototype or the first genetic disease that we found in which the actual defect in the genome was a bunch of repeats of this trinucleotide, cytosine, guanine, guanine, just repeating itself hundreds, maybe even like thousands of times. There is a certain types of ataxias, or basically cerebellar disorders or muscle disorders, which do not follow the classical Mendelian inheritance patterns either. And remember, not only do you have DNA in your nucleus, but you also have it in your mitochondria, right? And that's where most of the forensic DNA tests come from, is mitochondrial DNA, which of course comes from the mother, because the sperm has no mitochondria, maybe just a couple, but the maternal gonad, or the ovum, is loaded with mitochondria. There's also a concept of genomic imprinting, in which the presence of one allele inactivates the other. It doesn't just correspond to it, but it actually inactivates it. And then we also talked about mosaicism. So when a person has a genetic disease, it may only be in one group of cells and not the entire body. And the one group of cells that's most likely in only are the gametes. Okay, these are all non-Mendelian concepts. Once again, my son, who is a ophthalmologist, says that he has seen the Leber hereditary neuropathy, okay, which has to do with degeneration of retinal ganglion cells. And he's a retinal surgeon. Why would we want to use DNA probes besides regular diseases or tumors? Well, here's a bunch of reasons. If you take amniotic fluid and get some fetal cells, you can perhaps determine genetic problems by all these different techniques we've been talking about, even prenatal, not just postnatal, but prenatal. There's a very, very widening group of in pathology of taking the DNA and probes with regards to tumor cells, looking for mutations in the tumor cells. And those mutations may be why they are tumor cells. Also, for classification of tumors, you may have a certain tumor that has a certain name, but if there's a certain abnormal gene associated with that name, you can further classify it on that basis. You remember there's been all this talk about PCR with the so-called COVID pandemic. That's only the second time in 8 webinars that I use the word COVID, and if I get my way, I won't say it again. But PCR is an extremely sensitive technique because it detects technically the tiniest amount of DNA. So there are many false positives by the person who developed this test. He's saying if you're just looking at a tiny amount of DNA, it doesn't necessarily mean that that organism that has the DNA is causing the disease. That's why a lot of people have criticized saying there's been just a massively over-exaggerated amount of, I don't want to say the word, but it begins with a C. There are ways for donor compatibility for transplants and transfusions and that, and they've usually resulted or been performed by virtue of antigen and antibody compatibilities. But you can also make that much more stronger and safer by using DNA probes. Same thing with paternity testing. And of course, to look at DNA on the presence of a gun or a murder scene or whatever, that's another reason for using a DNA probe. And in this case, you're usually measuring the DNA of a maternal mitochondrial DNA. Okay? And here's an interesting concept that I was really sort of unaware of until recently, is that we know that malignant tumors can metastasize. And it's a big multi-step process, which we're going to dissect a little bit later. But when the tumor metastasizes, obviously cells have to get into vessels and they have to lodge in various places. So I think, well, a person that is told that they don't have metastases, either by x-rays or examination of lymph nodes, they feel pretty good. But, my friend Jim Liu, the guy who owns the lab that supports my webinars, the best and biggest molecular lab in Chicago and maybe the world, he says you can have actually tumor DNA that's found fairly specific for tumor, in the blood without having any evidence or metastases. Well, that would make sense because before you have a metastases, tumor cells have to float around in the blood. But guess what? It could also be free DNA. Pretty scary, isn't it? And finally, here's the last little image I drew, because this is a pathology course. And here we have a slide, which we're going to be seeing zillions of this year. The pink stuff is eosine, the bluer stuff is hematoxylin. We've diagnosed just about every disease you could imagine correctly just on the basis of this. But when you wanted to get fancy or you wanted to get more information for prognosis, we stained for specific antigens, which are proteins, by this ever-increasing art called immunohistochemistry. You're not just staining nuclear cytoplasm, you're staining antigens wherever. But now, this is something used in molecular labs called an array. And these little green and yellow and red, orange, blue dots are actually measuring the presence or absence of genes. So wouldn't it be cool if we call my age the old day of hematoxylin and eosin, the first level, and then the emerging good science of immunohistochemistry to make things even more accurate, and finally, rather than looking at the antigens or proteins, you're actually looking at the genes which are present or absent or abnormal, which code for them. So that day, I think, is coming. But I will tell you that even when we had the primitive H&E diagnosis, we got it right 99% of the time. Okay, we're done. Let's do our last song. Thanks for coming. I see there's still a really good number of you here. That makes me happy. And I don't know what our last song is going to be, but while we listen to it, we'll probably look at this beautiful girl again. And then we'll say our final closing 3 words, and you know what they are. and rock on too.